Let's take a look at the XYZ component method. Particularly still, we're going to apply this to particles. So we're going to talk about our XYZ in statics. We'll talk about the XYZ component method in two different ways. First is in terms of particle analysis, in which we do not consider moment impacts, rotational impacts like we would have in rigid bodies, and the other would be rigid bodies where we're going to have to get our moments in equilibrium as well, or make sure our moments are in equilibrium or come up to the designated resultant force. The XYZ component method is just like the XY component method, but now we're adding a third dimension to it, right? We're adding that Z or that K direction. We often use the XYZ component method with unit vectors because unit vectors are a way to separate our force magnitudes into X, Y, and Z components to get them into their vector format, right? First step is to draw a free body diagram. The second is to resolve the forces into their components, meaning to break each force down into its X, Y, and Z components. Then we'll write our equilibrium equations. In the XYZ component method for particles, we will have three equations. That would be the sum of the forces in X, Y, and Z direction. The last thing you're going to do is you're going to solve for your unknown values. If we're looking for a resultant, then the sum is the resultant. If we're working with an equilibrium situation, then all of the force equations should sum to zero. The summation of forces in the X direction should be zero, summation of forces in the Y direction equals zero, and summation of forces in the Z direction equals zero. So for our example problem, solve for the unknown values, knowing these three force vectors are in equilibrium. Unknown values are A, B, and C. We have three force vectors, each with an unknown value. Force 1 is 1i plus 3j plus ak. Force 2 is bi plus 2j minus 1k. Force 3 is 4i plus cj plus 5k. We can separate each force because each force is in its vector format. It's easy to separate them into their x, y, and z components. If we're working with an equilibrium situation, which our problem statement tells us that we are, we know that the resultant force is going to be equal to zero. That means that the resultant force's x component, y component, and z component will all be equal to zero. This gives us enough to write three equations, the first being our summation of forces in x, where 1 plus b plus 4 equals 0, giving us b equals negative 5. Our summation of forces in y, giving us 3 plus 2 plus c equals 0, giving us a c value of negative 5. And our resultant force in the z direction equals 0 is a minus 1 plus 5, which gives us a equals negative 4.